All right, everyone, we're gonna speed through these. So first off, I'm gonna do 12 and 16 again, much more simply. So here's the deal, right? For 12, right? Basically, what's going on, right? You got your if your rate constant's too high, your rate's gonna be too high. So that's how it works. It's about having a super high rate. Then you figure out the rate constant, not the other way. So if there's too little HCl, then you're gonna have right your K rate equals K times stuff. So too little stuff, so your rate's going to be too low, right? Perfect. So that makes your rate constant too low. Your rate constant is going to be lower. So one is wrong. So uric acid delays, right? Delays the reaction. So when there's less, I2 reduce faster. I2 is formed more quickly, and starch iodine complex formed more quickly. So it's faster. So 12 is B. All right. Next. 16, quick formula. You guys are going to want to know for density equal of a unit cell, mass over volume, number of atoms times molar mass over Avogadro's number times volume. Volume equals edge length cubed. For FCC, radius equals root 2 times edge length over R, not over R, over 4. Okay, 1 pm equals 10 to the negative 10 cm. Okay, plug this stuff in. 139 times 4 over root 2, which is 2 to the 1 half on your calculator. Now you're going to multiply that by 10 to the negative 10. So 3.93 times 10 to the negative 8 centimeters. So cube that. Multiply by 6.122 times 23, 10 to the 23. And now you're going to do 4 times 195, which is the molar mass, and divide it by 36.59. So 21.31. Perfect. All right. So that was that. All right. Next questions. All right. Let's go really fast here. Because you only got, what, 70 minutes on the exam, I think? Or an hour? I'm not sure. Okay. Uh, okay. So 21, really simple. State functions like enthalpy, Hess law, thermal cycles, right? It doesn't matter how you get to the value, you're going to get the same value. Path functions are the opposite. These are path dependent, mostly work and heat. That doesn't mean that work and heat, you can't have them independent of the path taken, however, right? Because here you got, for one, you got a fixed reaction. So you got a fixed delta N. Why does that matter? I'll show you. And you got a fixed pressure, right? Work equals negative P delta V. So that's also the same using the ideal gas equation. That's negative nRT or negative delta N times RT. So if in a reaction, you're going to have a fixed delta N. Perfect. So you're going to have a fixed value for work. And then 2, heat absorbed by the expansion of a mole of carbon dioxide. Well, for this, you don't know how it's happening, right? Because heat works in different ways, right? You have a gas expanding, pressure decreasing, right? So if it's adiabatic, right, it's going to be Q equals 0. If it's isobaric, it's going to be integral. It's going to be integrated from the constant pressure molar capacity, otherwise known as CP, C sub P, right? If it's isothermal, it's going to be nRT ln of Vf over Vi. So you don't know which way it's going. You would probably assume isothermal, but you never know. It's not isobaric, but it could be adiabatic. So you're not sure which path it's taking. All right, 22. I want you guys to follow what I say. It's reactants minus product, but it's also equal to a negative value. So it's going to be reactants equals products minus that value. And you're going to subtract what you know from reactants, right? It all makes sense, basically, right? You find the reactants, right? So C3H6, draw it out. It's an alkene. You're going to have one double bond, not two, which is a cumulene, right? So basically, okay. So you're going to have one double bond. Okay. 345 plus X plus 6 times 415 plus 4.5 times, be careful, 2, no, it's just 1. It's 100 bond. 498, perfect. 5076 plus X, and 3 times 2 times C double bonded to O, because that's CO, 2, plus 3 times 2 times 464, perfect. So now you're going to add 7608 to negative 1926. You get a value and subtract 5076, that's your X, so 606. Fast. Alright. Quick. Okay, so let's see. Alright, we don't got time, right? 70 minutes. Which reaction has delta S greater than 0? Well, actually, I'm curious. How long is the USNCO Part 1 exam? Oh, really? Okay. Oh, I guess we got time. Anyways, what reaction has delta S greater than 0? Obviously not 1, not 2, because graphite is a lot more ordered than just the buckyballs, even though it's more. This is about aqueous stuff, so pay attention here. Water forms cage-like structures around ions called clathrates. These are very ordered, like super ordered, right? So in C, these are being formed. D, these are being broken because H2O is being released. So since order is less, right, it's being destroyed, or not necessarily destroyed, but like, I don't know how to say it, just removed. Let's see. All right. This one is a quick one, right? Sample, you got 110 grams total. You gotta be careful here. There's no Q in and Q out. It's more like Q total for one system. The system is the ammonium nitrate and water solution. So it's 15.1 minus 22 times 4.184 times 110 grams total, right? Now you're going to negate that and divide it by moles to find delta H. It's a classic formula. So negative of that divided by moles. So moles of limiting reactant. Obviously, the ammonium nitrate is the limiting reactant because 10 over 81 over 80.1 is much less than 100 over 18. So you're going to divide. Don't forget your negative. Doesn't even matter here, but yeah. So you get D. All right, this one. Very fast. Okay. Forget all this. You don't need to read any of this, actually. Uh, Boom, right? Basically, order in H2O2. Skip H plus right now. Order in I minus. Look at these. I minus, you got 1 and 4. So if the time is halving when you double it, then its reaction rate is doubling. So it's 1, right? But H2O2 is what? Well, same thing. We choose reactions. No, H2O2 is 1 and 4, and I minus is 1 and 3. Same thing happening, roughly having the time, right? Okay, so it's either C or D, C or B or C, right? So H plus, that comes from our ascorbic acid. You might want to read it to give a little bit of context. It's the starch iodine complex we talked about before. So look at what's happening. Do reactions 2 and 1. Time is staying relatively same, so it's B. Oxidation is cyanide ion, blah blah blah. Okay, simple rate. you're going to want to write these two equilibriums. K1 equals HOI over H plus times OM minus. K2 equals OH minus times ICN over HOI times CN minus. Beautiful. And K times ICN minus times OH is the rate because it's a slow, it's a RDS, rate determining step. So look at what's going on, right? In the third equation we wrote, we had the small k. First two, it's the big K, the equilibriums. So ICN minus times OH, what is that? That's K2 times HOI times CN minus. Multiply that, and now look at this. What is HOI? It's K1 times H plus times OI minus. It's a lot, but if you followed what I said, you would know that the rate is CN OI, sorry, OI, okay, OI times H plus. Okay, perfect. Because what's going on, right? First, you use the second equilibrium to replace ICN minus and OH. You got OH, HOI minus, and you got HOI and CN minus. HOI is another K times H plus times OI minus. So a small K and two big Ks, they all make one big K, one small K. Okay, and keep reading the question. pH is greater than either pK. So that means the H plus is small, but that should not trick you to pick A, because if it's small, it's still being considered. Alright, so that is that. Okay, next one, right? Okay, so as you can see, this is simple solve. So we have something decaying into something else, which is decaying into something else, and we're trying to find the half-life of that intermediate, right? So how do you do that? Well, you just do this. Very simple formula, common sense. Half-life equals decay rate minus formation rate. So what is the decay rate of Br? Okay. The decay rate of Br is basically, well, take a look, right? You have here 60 at 60 milligrams, right? You see, um, basically what's going on is it's 38 seconds. No, sorry. Yeah, 40 seconds, 40 seconds. 40 seconds, 38 milligrams. 40 seconds, 60 milligrams. 100 seconds, about like 36 milligrams. So if in 60 seconds it's almost half, you can say 70 seconds it's going to be fully halved. You can think about it proportionally. If 60 seconds is 60 over 36, x seconds is 60 over 30. So I guess you do proportion and you get like 72 or something. But now you're going to subtract the formation, which is the half-life of SE. So that's going to be what, like 16? So 70 minus 16, basically 55. Remember, we did approximations here. Okay. I'm going to do 29 real quick because I like it, and I'm going to go to 28. Reaction of tert butyl chloride with azide ion takes place via carbocation intermediate. Classic SN1 reaction. We have a tertiary substrate, I guess. Yeah, definitely not ideal for SN2 because of the steric hindrance. Azide ion takes place. Okay. The reaction proceeds through. Okay, high polarity. Yeah, that makes sense, I think. Solid line represents a solid reaction according to 80% water, 10% ethanol, 20% water, 80% ethanol. So there's less of the polar solvent, so it's going to be slower. So you're going to have a higher activation energy. So let's look for the one that has a higher activation energy. The dashed line, right? This is a wait a second. Faster in solvents of high polarity. So it's going to be slower. So basically, think about this. Right? Um, so if it's slower, then look at what's going on here, right? Activation energy is from reactants, transition state. Here it's lower. This one is higher, that's true. Okay. This one is lower. Okay. Usually it's the transition state whose energy gets higher, not the reactants that gets lower. That doesn't really make sense. It's always the transition state, so it's C. Alright, perfect. Okay. Oh boy. Okay. I have the setup here already. I'm gonna explain this to you. Right? If you read this, there's two reactions going on. Shoot. Okay. R to X and R to Y. Perfect, right? So for these, right, all that's going on basically is 50% X and 50% Y, and now you're trying to find out the yield at 70 degrees Celsius. So at 50 degrees Celsius, 50% Y and X, it's whatever, equiproportional, I guess. 70 degrees Celsius, we gotta find the right amount, right? So if you think about K2 being for Y, the concentration of Y, and K1 being the concentration of X, that is really helpful, right? So, okay, now this goes back to here. Beautiful equation. See this? This is the equation you guys need to know. You can rearrange the temperatures. If it bothers you, T2 minus T1, you're gonna have to put a negative here. Okay, let's go. Yeah. So just plug this stuff into this equation, right? So ln of, let's call, you know what? Forget about it. Let's call this K2 to K1 ratio X. You know, let's call it W. Ln of W equals your activation energy difference, because you're subtracting equations theoretically. Be careful, please be careful. This is 20 kilojoules. So 20,000, you're going to write 20,000 times 1, okay, be careful here, right? 1 over 273 plus 50. And you have 1 over 273 plus 70, right? Now you choose. I'm going to do 50, I'm going to do the first one minus the second one. And I'm going to multiply it by 20,000 and divide by 8.314. Now I'm going to raise e to that to the power of what we get. We get 1.54. Okay. So we have K2 to K1 equals 1.54. What does this tell us? Well, it tells us that one of our proportions is 1.54 times our other proportion. So how do we figure this out? Well, if they both add to 1, K2 over 1 minus K2 equals 1.54. Plug that into your... you know what? You can just solve on your own. K2 equals 1.54 minus 1.54 K2. 2.54 K2 equals 1.54. K2 equals 1.5 over 2.5. Approximately, forget the 4s. So K2 is about 3 over 5, which is 60.6%. Basically, I'm assuming. Yeah, and K1 is X. K2 is X, sorry. Yeah. So we're going to get, because if you think about it, we're trying to solve for yield of X, right? So we put X as K2 at the top. So yeah. Okay. So 60.6%. This question was my favorite one on the entire exam. So reaction of, because it's kinetics and Orgo. So that's really good combination. Reaction of hydroxide ion with methyl iodide. The action is faster when the carbon 12 isotope is present than when carbon 14 is present. Okay, this is something called the secondary kinetic isotope effect. Cool. Okay. Okay. So we got a strong nucleophile, a hydroxide ion, and methyl iodide. Iodine's a good leaving group. Methyl, okay, not too bulky. Now, carbon 14, carbon 12. Okay, carbon nucleus not stable. There aren't radicals here. There isn't any decay. It's not like isotopes going on here, like radioactive isotopes. There's a negligible difference in stability. Okay, chat. Let's move this. All right, all right. What else? Vibrational energies. Okay, let's skip that right now. Molecules less sterically hindered. It's such a tiny difference. It's a minimal mass difference. It's such a tiny mass difference. You're adding 2 neutrons. That's not really gonna make a difference. Carbon iodine bond dissociation enthalpy. What does that have to do with anything? It's the same atom, just a different isotope. Vibrational energy. So what does this mean, right? Well, a bigger molecule in general, whatever, it's gonna vibrate with lower energies, right? You're going to have a lower 0 point energy of the molecule because it's more molecularly bulky, not steric, right? Okay, so then what you're gonna do is, well, if there's a lower 0 point energy, there's gonna be a higher activation energy. That's the correlation, right? So it's gonna react more slowly. So it's gonna be, yeah, a lower rate constant. Perfect. So that's what the vibrational energies are. When you have a molecule at rest, it's still vibrating, right? That's the 0 point energy. The lower it is, because of more bulk, it's going to have a higher activation energy to cross, to react. So yeah, that's pretty cool. I like this question. So yeah, that was up to 30. All right.